Okay, today I would like to finalize the topic for singly linked list because I think the exercise you do for lab number 5 is rather easy. Hopefully after the lecture, you can solve that pretty easily. But I'll give you some more guidance about how you can prepare for lab test 3, which will be next week, right? Okay, but let's now finish the topic about singly linked list. Let's try to finalize using 2 exercises over here. So now let's say we are trying to define 2 methods over here. And in the context of the singly linked list, we got 3 attributes. Remember, you got head, we got tail, and we got size, right? Now, I want you to think about just in English, in your natural language, how you would do, just step by step. Let's say we have this method over here. It's called insertAfter. It's a mutated method. You're taking 2 parameters over here. You're taking, what is that? Well, sorry about that. I'm not even sure where that comes from. Actually, that's weird, right? Could be. Oh, Halloween, right? Okay, that's really unpleasant. Okay, anyway. Okay, forget about the interruption. Okay, so now let's go back here. Let's say we are trying to implement this mutator here. It's called insertAfter. You take 2 input parameters over here. The first one is we're taking a reference of a node. And what we want to do is we want to insert after this particular node with a new node. And the new node is going to store the second input, string E. Okay, that's the first method we want to have. Just take about a few seconds to think about how you might do this method here. And I'll give you a little bit hints. This is kind of the setup you should have before you design the implementation for this. So again, we are trying to do insertAfter over here. And we have, first of all, the parameter called n. You can think of n is simply some reference to some existing node. Okay? And the node is simply storing something. And then you can see, in general, the node can be just part of some chain of nodes. So the node has some previous node over here. Also, it has the next node over here. Okay, that's kind of the setup. What we want to do is, we want to have, so the second parameter you have is E over here, the string. How can we insert after this particular node, another node, which is going to store the string E? What would be the necessary steps to complete? And at the same time, I want you to also imagine what would be the complexity for this method here. Okay? Any idea? I kind of gave you the simpler one. I'm going to compare 2 different methods. This is the simpler one. Yeah, go ahead. Okay, 2 steps. Which 2 steps? Just say them. You create a new node. Why don't we do that right away? Okay, I agree with that. So now somehow, and I'll leave the Java code to you. I'm just going to draw the diagram, and then you should know how to do the corresponding Java code. Let me use green. Okay. So the black over here is actually what you are supposed, what the program gives to you as input. And then the green part is going to be what you have to implement. Okay? First of all, we're going to create a new node. And the new node is going to look like this over here. And the new node, let me call it NN, new node. And then it's going to point to some node over here. And then we have also elements and next. So now, what should you do for this new node? Okay, the element should point to over here, which means nn dot elements should be assigned to this element, okay, element here. Okay, I'm just sketching the idea for you. And then, okay, that's step number 1. And then, okay, what about I do the rest? Okay, how? Okay, so now how should we set the next reference over here? You can see the node here, by default, the next reference here is simply null. How should we set it? So that it will be inserted after n over there, right? So what we should do is, over here, nn dot set next. What should that be? In this case, n dot get next, right? This node over here, okay? N dot, I'll just say n dot next. Okay, so if you do that, that means this is going to point to this node over here. Okay, are we done or not? No. One more step. Ken?
Set n.next to the node that you just created.
Exactly. That's really to complete the insert after. So now in this case, what we got to do is make sure. Let me just use a different color here to say this is also important. So n.next, rather than pointing to here, it is going to point to this new node. So n dot set next is nn. So these are exactly what you got to do in the Java code. Yes. The size, good question. And then, since we're adding one extra node, so you should also say, since size is an attribute, very good point. You got to say size plus plus. So now you can see that the way you think in terms of diagram, each step corresponds to some line of Java code. So that's the technique I hope you can learn. Okay, now, what's the complexity? I don't know why. How can I turn this off? I'm not sure, actually. There's nothing running on my computer, right? Oh. Okay, anyway, yeah. Maybe, okay. Now, what's the complexity of this method here? Would it be big of 1 or n? 1, because we got only 3 steps always. We never actually reach a loop. So the complexity of this method here does not depend on the size of the chain, right? So that's going to be constant time. Okay, very good. Okay, so this is exactly the step we just described, constant. Let's consider a second method here. Now, let's say the second method here, rather than insert after, we have insert before. Okay, and now you can see the parameters we have over here are the same. We also got some reference node n, and then we have a string over there. We want to insert before that. Okay. Now let's see the setup over here. Okay, you can see the diagram here. We got pretty much the same beginning points, but now how do we do it, right? So now you can see that the node that we're going to create, so step number 1 for sure, it will be, we have to create a node. Let's do that first. You have to say a new node over here, let's say it's called nn. It's going to be a node, and then the element is going to point to E over here, right? Now, what should be the next of this new node? If I want to insert before n. You want to find the previous node, right? So somehow this node here is important. This is really the key. Thinking this way. If you want to insert before n, it's as if you try to insert after its previous node. But how do you know what the previous node is? You wouldn't know, just given the input that you were given, right? So how can you find that? You have to somehow use a loop by using current to say until current.next is equal to n. I'm going to show it to you, okay? So let's say over there, I'm going to show you, that's the key. So let's say you have node current starting from the head of the list. And then you would say while current dot next is not equal to n. So this is really the key. While current dot next is not equal to n. So that's the state condition for the while loop, which means as soon as it becomes n, that means we're going to exit from the loop. Okay? And then inside the loop, we're going to say current is assigned to current dot next. Okay? Let's say now, when we exit from this loop over here, we know that at this point, current dot next is exactly equal to n. Reference comparison, right? So now we know that this is current. Okay, let's complete the remaining parts. What should we do? Ken? Yes, that's one way to do it. You can say insert after. Very good. I like that. So there are 2 options over here. You can either say, I'll give you 2 options. That's very good. Option number 1, you can say insert after, and then you can say current, because that's already current.next is already n. Current and then E. That's certainly a better solution. Okay? Let's try to be a little bit naive. Let's say you didn't realize you can reuse the code. How would you do it? And the second way, how about we just do it again? You have to somehow say current.next is set to be nn. And nn.next is set to be n. Right? That's what you would do. Okay, let's write it down, and then I'll draw the diagram. So for number 2, it's going to be here. It has to be current dot set next. That should be nn. And also nn dot set next should be just n. Right? For this line over here, current dot next, rather than pointing to over here, is going to point to nn. And then nn.next, rather than pointing to null, is going to point to n. Okay, you can try to redraw the diagram to make it more organized, but hopefully that illustrates the idea. So now let's talk about complexity. Okay, overall, how many steps do we have? Let's try to use a different color to illustrate. This is the very first phase that we did. We just want to find out what is the previous node before n. And then the second one is over here. You can have either of the options. So now what's going to be the running time for this? Is it still going to be constant or linear, right? Because you can see the phase number 2, since we can call insertAfter, it's guaranteed to be constant. However, that running time is going to be dominated by the phase 1. And what's phase 1? It depends on where n is, right? If n happens to be at the very end of the chain, in that case, you have to traverse so many nodes before you can get there. In that case, it will take exactly n iterations to get there, right? So for number 1 over there, it's going to be linear. And for number 2, it's going to be constant. And overall, we got linear. Okay, okay, that's basically what you have to do for the second one. Okay, any questions about this? Yeah?
I feel like if you don't know what the reference is for the nodes, that could be like an NPM.
Ah, okay. So the assumption over here, yeah, of course, what you could have done is, as part of the precondition for this method, you can check to see if there's any cycle over there. But for simplicity, let's assume that's not the case. Yeah, but it's a very good concern. So the question was, what if the chain we have looks like something like this? For example, let's say I'm just adding a new thing over here. Let's say for insert before or insert after. Thank you. Forgot about that. Good. So now let's say for insert before or insert after. Let's say this is the end you're given over here, and somehow it has a cycle maybe, right? So in this case, how can you break the cycle? Let's not worry about that. You may have to worry about it in 2011, not this course. Okay. For simplicity, we assume that's not the case. Okay. Assumption is there's no cycle. Okay. Any question about these two methods? Okay. So I would say you should really get a basic sense. Every time when you're trying to do a method for singly linked list, if somehow you have to go to a particular node, starting from the beginning, it's going to be linear because you got to use a loop. If you can simply just by setting some references without using a loop, it's going to be constant. That's typically the case. Okay. So far we have seen quite a bit, almost maybe 6 or 7 methods for singly linked list. That should be enough. Not only for completing lab, I'll give you some preparation exercise on Thursday, so you can do preparation for lab test 3. Okay, one more slide I want to show you over here before we move on to a new topic. So this table here summarizes all the basic operation you will normally do, and we try to compare what's the difference between the complexity of array and singly linked list, right? So for example, you can see that if you want to simply get a size or get the first or last elements for both array and linked list, it's rather easy. Because for linked list, we got head, we got tail, we got size, right? It's all constant. But now I want to draw your attention. You can read the table in detail later. Let's see, for example, it'll be interesting to see remove last, right? You can see remove last, it is simply just bigger of 1 for array. You can simply assign the last slot of the array to be null. That's constant. On the other hand, how do you remove the last elements in the linked list? Since it's singly linked, you have to go all the way to the second last, which takes linear time, and then set the references. Okay, that's why it's linear time over there, right? That's kind of draw the comparison. You have to be very careful. We're going to see that in the next topic. Whenever you have to use a remove last method for the singly linked list, it's going to be expensive. It's going to be linear. Okay? And also, you can see that if you try to add, remove some elements in the middle, you have to shift everything to the right in the case of the array. In that case, that'll be linear. On the other hand, if you are given a reference of the node and you simply want to insert after, for example, in that case, it will just be constant, right? So you got actually, it's quite a thorough comparison. Read it through and make sure you got it. Of course, don't memorize it. Okay? It's only for you to reflect and think about how different operations work. Any question about singly linked list before I move on to a new topic? Yeah. They're pointing to the position already. Yeah.
So is that done like when you're making the list? When you assign this?
Good question. So remember head and tail, they're attributes, which means when you first create a singly linked list, they are simply just null by default. As you're adding more and more nodes, each time when you're adding a new node, you can see at first or at last in the slides. Every time when you're adding a new node to it, you want to make sure you keep those references up to date. Right? For example, let's say you're adding the first, what you need to add update would be the head, not the tail, right? Things like that. Yes, correct. If you have only one element there, it's both the head and the tail. Yes. Okay, so now we're going to move on to a new topic. It's rather easy, it's stack and queue, before we move on to recursion on Thursday. Okay, stacks and queues. We'll try to do some application of linked list and also array, which means for stack and queue, for different ADT abstract data type, I'll review what it is in just a moment. We can see that every time when we want to implement a particular function, we have at least two options there. Either you can implement it by singly linked list, or you can implement it by array. But now you should have enough knowledge to judge which one would be better. You should know where the bottleneck is. Okay, that's something we'll try to exercise together. Okay, let's now go on to stacks and queues. They are very easy concepts. I'll rather focus on the application of these concepts. But let's go just define what stacks and queues are. What is a stack? First of all, it's a collection of objects. It can be a stack of strings, integers, accounts, or person. Okay, stack of objects. And then this is the most important property you have to remember for stack. It's called level property, last in, first out, which means whatever that goes into the collection the last, when you try to retrieve something out from the collection, that element will be retrieved the first. That's why it's called last in, first out. Okay, we'll see how useful this can be actually, stack. And when we talk about recursion on Thursday, we'll also use a stack idea. Okay, so make sure you understand stack very well. Okay, so now the thing is, for the stack, also it's easy because the only thing you can get access to it is the top stack, which means the one that you inserted to the collection the last, the most recently inserted. Unlike array, for array you can get access to any arbitrary position, but for stack you cannot. You only access to the top conceptually. I'll draw a diagram in just a moment. Okay, and let's see some real life example. So you actually got lots of example like a stack. For example, if you go to buffet restaurants, the plate you actually get should be the one that was put on the pile the last, right? That's kind of one example here. And this one here, I'm not too sure if you have tasted that before, right? If the candy, if you're loaded, the one you're gonna taste will be the one you just loaded the last, right? Also the same idea. Okay, now let's talk about stack. Let's talk about the ADT. Again, ADT stands for abstract data type, and you'll learn more about it in 2011. What you need to know about abstract data type is every time we talk about particular type, for example, stack, you have to know what kind of methods or operations you have to support. Okay, let's see what operation you're going to support. And you can see now the interface means the methods we want to support. We'll see that in a moment. And for the data structure, you have different choices. In this case, we're going to see both array and singly linked list. We can actually see which one is better for us. Okay. Okay, we got accessor here. We can query about the top. So let's learn some terminology here. So the most recently inserted element into the stack is called the top. And then we got something called size, the number of elements in the stack, and also if the stack is empty or not. How about mutators? How can we modify the state of the stack? Something called push and pop. Okay, it's a very specialized term, push and pop. You do not say insert and delete. Insert and delete are way more general than what you can do for push and pop. Push and pop are very specialized operations. Okay, the push and pop. Let me show you how the stack works. It's very easy. Okay, so now let me just. Okay, we don't need this anymore. Okay, let's think about what the stack operation is, and I'll contrast that with also the queue in just a moment. Okay, stack operations over here. You can do basically push, pop, top, and size. Okay, let's say we focus on these operations. Okay, this is how I would draw a stack. Initially, this is how I would draw it. So this is empty stack. Nothing there. There's a reason why I draw it this way, you will see. Let's say I'm trying to do the following. Let's just call this stack S over here. If I say S dot push, let's say we talk about a stack of strings, Allen. What you would do is, it's going to simply put it on the top of the stack. But now it's special because it's just empty. So we just push that into the top. So Allen is on the top. Okay? Let's try to ask some question about a stack. If I say, for example, S dot top, what would it be? Just Allen. That's quite obvious, right? By the way, when the stack is empty, you cannot query the top. It will be a precondition violation. We'll see that in the code. Okay? Let's just focus on the more general operation. In this case, it will simply just give to me Allen. Okay? So that will just give me Allen. Okay, let's try something more. Let's say we try the following. Let's say S dot push. Okay? And now let's say mark over here. And now let's see how the stack will look like. So now Allen used to be the top. And now Allen is still here. And we are not trying to replace Allen. We'll simply stack on top. So this is where mark will be. The interesting thing is, remember what's the definition for top? The most recently inserted elements. It's not Allen anymore, it's now mark. So now if you try S dot top, that will be mark. Okay, good so far? Okay. Now let me do another one, and I'll show you some remove operation, like a pop. Let's say we try again. Let's say we do S dot push, and then Tom. What I will get is something like this. I have Allen, and I have Mark, and I have Tom, like that. And now, of course, if I say S dot top, it will be Tom. Okay. Now let's talk about the operation called pop. Pop is a little bit tricky. The pop is going to do two things. Okay, I'm going to write it here. The pop over here is going to, first of all, remove. Let me put it in this order. That might be easier. You can think of it's going to return the current top. And at the same time, it's also going to remove the top, which means it's going to return whatever it has just removed. Let me give you one example over here. Let's see over here. If I say S dot pop, so what does it do? It does two things. It's going to, first of all, return Tom, which is a top. At the same time, it's also going to remove Tom. So whoever is calling the pop can capture the value. You will see this method is here. It's very useful. Okay. What you will get, first of all, is you have the stack now becomes Mark being the top, and the next one will be Allen. And then S dot top. Oh, sorry. Let me see it. At the same time, this S dot pop is going to return Tom. No, actually it's a pop, right? So you're going to return Tom. Okay. Okay, maybe this is a little bit confusing. I'm going to use a blank page again. Let's try again. Let's say we are focusing on this particular stack over here. We got Tom, Mark, and Allen. Tom is the current top. When we say s.pop, it's going to return Tom and remove Tom at the same time, right? Okay, that's what it is doing. You might be wondering why this is useful. You will see in very soon, okay? So now, let me ask you one more thing, okay? Given that, let me just use a new page to ask you a question to test your understanding. But any question until now about push and pop? Yes?
So push takes a parameter, but pop does not.
Exactly. You know why? Can you try to explain why?
Because it's always gonna pop out the
Top element, so there's no need for any extra inputs. It's a very good question. Let me just finish that and then I will answer your question. So the question was, why does the pop take no parameter, whereas push takes one parameter? It's because when you push, you want to know what new element you want to push onto the stack, so you need some extra parameter. On the other hand, for the pop, you know it always is you're going to pop this top of the stack, so there's no ambiguity, so you don't need to take any extra parameter. Yeah, question?
Shouldn't the pop change the top element? You're removing the top element, so now it's nullified. So shouldn't it
You're thinking a little bit too much towards the implementation. Let's worry about null a little bit later. We're just talking about diagram, just for your intuition, but we'll get there. Because you see, what we're talking about on this particular page here, we talk about in general how you can do the different operations, but how can you support these operations? You can support it either use linked list or array differently, okay? So now we talk about two levels of thinking. The first level is intuitive level, abstract level, like a diagram. The next level we're going to get into, we got two options, either using array or linked list. That's what we'll get into, okay? Okay, let me test your understanding here very quickly. Okay, let me just add another page over here. Let's try the following. If I say, let's say we got a new stack. Okay, S is empty at the, to begin with. Stack, let's say empty stack, S over here. If I say S.push, let me just say Alan, Mark, and Tom again. Alan, S.push, Mark, S.push, Tom. Okay, now, we know that what this will get is Alan, Mark, Tom. Now, let's try the following. What if I do 3 consecutive pop? If I say S.pop, 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 what it will give to me in sequence? Tom, Mark, and Alan, right? Can you see any interesting thing about this? It's going to give me Tom, and then Mark, and then Alan. Can you see any special thing about this? What's the sequence in which you insert Alan, Mark, and Tom? It's Alan, Mark, and Tom, right? Now, when I pop things back, it gives me the reverse, right? That's exactly the property for last in, first out, okay? Hopefully you can see that, right? Okay, so now you can see that it's in this order here. So this over here, the reverse order for pushing, okay? Any question about this? And one more question for you. Let's say after the 3 consecutive pop, if I say S.size, what would that be? 0. Good. Just to make sure. Okay? Because every time you do the pop, it's going to actually return the old top and also remove it. Right? Okay, very good. Okay, this one you pretty much get it. So just another example. So I can skip that. So stack is very easy over here. So let's now think about how we can implement the stack ADT. I'm going to show you 2 different implementations. One is array, the other one is linked list. Okay? Now for the array idea, it's very similar to how you did for your birthday book exercise or point collector. Remember, we got a single array, and then we have something called number of entries or number of points. Okay? But now we're also going to use some integer counter over there, but the initial value is going to be a little bit different. Okay? But the idea is very similar. First of all, let me explain what the idea is, and then the code is very easy to follow. Okay? Let's now see how we can do that. Okay? Now let's see how we can do the array implementation for that. And the way we do for the queue is completely symmetric. So that one I can just leave that to you. Okay, let's try this. So now we are trying to implement a stack using array. Okay, so now how do we do that? So now, how do we do empty stack? Okay, let's say initially, let's say this is something I just call data to be consistent with the name I have in the slides. Let's say we have some data over here. And let's say the maximum number of elements we can store in a stack would be 1,000, for example. So we got 0, we got 1, we got 2, and 3, etc., up to 999. So the maximum capacity is 1,000. Okay? And now there is a special counter we have called t. So t is an integer. So that simply means the index of the top. Okay? Which means if the t happens to point to index number 1, that means the top of the stack is at element number 1. Okay? How do you think the t value should be initially for empty stack? We cannot give 0, of course, right? We should give something that doesn't make sense, right? In terms of indices. How about -1? -1 makes sense. Okay? The reason that it cannot be 0 is because, so now for this particular implementation, what's really good about it is every time if you want to return the top of the stack, you can simply return data at position t. That's what you can do. But initially, because the stack is empty, so it cannot be any valid index. Okay? So now for empty stack, t is simply going to be -1. So this is empty stack. Okay, that's the initial value. Now, let's try to see how we can do push. It's actually very easy. Okay, let's see what happens when we say stack.push, and then we say Allen. Now, what we should do is we should somehow update the index over here, right? The t, maybe increment it from -1 to 0, which means now the top should be stored at position 0, and then store the string over there, right? So there are two things we should do. Over here, we should say t++, and then data at position t should be assigned to Allen. So what does it do? First of all, when you say t++, that means it's not going to point to here anymore conceptually. It is going to point to the first position here. T will now be 0. And then store Allen over there. So now let's do one exercise over here. What happens if I say s.top? It should be Allen, we know that, right? But how do we figure that out? You can simply return data at position t, right? It will just give you Allen. Okay, follow so far? Let's do one more push. Let's say we do another one. Let's say s.push. Let's say mark. We do something very similar. We have to say, if you see that we do the increment first, we cannot do the assignment first, right? Because that's going to override the current top, right? So now what we should do is similar. We're going to say t++. Okay, let me use a different color here to really show you the contrast. We're going to do t++ over here, in which case it's going to now conceptually point to the next position, which is 1. So t is now 1. And then we say data at position t is now assigned to mark, right? So now it's going to be mark over here. So now if you try another one, let's say s.top. It's going to be, well, simply just return data at position t. In this case, because t has been incremented to 1, so it's going to return Allen. Oh, sorry, mark. Yeah. Any question until now, just for push? Okay? You can see it's actually rather straightforward. Somehow, we are treating whatever the position that's being pointed to by t as the top. That's a key. Initially, that should be -1, simply because initially there's no top. Okay? It's a very good question. Yes, in general, the question was, when we try to insert when we try to push a new element into the stack, what if the current top is already at 999? In that case, if you increment it, it's going to be 1000, which is not valid index. Of course, you got to check. It's going to be a precondition violation. We'll see that in the code. Very good. Okay, let's just try to do let's see how we can do pop. Okay. Let's just see one example here. Let's see when we say s dot pop. Okay. What should we do over here? Anybody want to try? How should we do pop? You can just return data t. That I agree with that. But if you simply do that, remember pop is going to remove the top as well. It's not actually pop, not top. Yeah. So how do you actually implement the operation where we remove the top?
But doesn't it remove the top as well?
No, it doesn't. So what Raymond just suggested was something like this, which should be part of the step but not complete. Over here, what we can say is, for example, if you simply say return the data at position t, it doesn't really change t, does it? It does not change it. So if after this method call here, if you try to do s.top again, it's still going to return mark, which is not right, because mark should have been removed. By just missing some minor details here. Anybody want to complete it?
What if we save it? Let's say we save it first. Save what we're returning.
Yes, you may save it first.
Yeah, and then we remove it.
That's also fine. Yeah, I'm just trying to see that. Yeah.
Yeah,
Yeah. Go ahead. Yeah.
or you could just do like t minus minus and then return.
Yep. That will do. Yes. Do you want to say something? Yeah.
Let's say decrement t.
Decrement t, exactly. That's exactly the point. So you should really notice that for pop, decrementing the t is very important. So now when you see over here, when you say t minus minus, but I cannot return data t anymore, can I? Right? So what I would suggest is as follows. We can say string ot top, okay, is assigned to data t. And then minus minus, and then if you want to be very complete, you can also say, okay, let me erase this. Okay, let me do it properly. Okay, there are several things we want to do. Let me show you the most complete version. So this is what I want to do. I want to say string ot top is assigned to, you can simply say top, right? You're just calling the helper method, right? That's one way to do it. Or you can say data t, either way. After this, we can say that data t is assigned to null. This is not so necessary, but what I'm trying to do here is, I'm trying to say mark is gone. So this slide is going to store null only. And then I'm going to say t minus minus, which means now t is now going to be shifted back to t will be 0 only. And then I can return. Return the o top. Okay? I would say this step over here, okay, that's a bad color. This step over here is not so necessary, but it's up to you. But I would say it's cleaner because you're really saying that whatever I'm trying to remove, I simply set it to null. Okay? Any question? Yes.
If you don't set it to null,
Okay, I tell you why it is fine. Because remember, every time when a user wants to access the stack contents, what can they access? Only the top. And the top depends on what t is. Since we decrement t by saying t minus minus, so t is guaranteed to point to the right spot, right? Mm-hmm. Yes?
so if we use step point here, should it be set to 0?
If we try to say it again.
So if we use step point,
Yes, very good question. The question was, so here we talk about stack of strings. String is a reference type. That's why we set it to null. What if it's actually a primitive type? In that case, set it to the default value. If it's integer, 0. Double, 0.0, right? And then Boolean to false, things like that. Right? Good question. Okay, so now let's see the code. Since once you understand this idea here, the code is not difficult. Okay? So and all the source code is also available on the course website. You can import the project and then play with it. Okay. Also got JUnit test for you. You can play with the code. Okay, we got some capacity over here. And then we have a data stack array, exactly what I just illustrated. So now the code should not be difficult. And we got T over here, that's a top index. And then when we first create a new empty stack, initialize the array and set the T to be -1. Okay? Question for you, how do you implement the size method? Since now we don't have number of entries or number of points. Good, T+1. Exactly, right? You just cannot return T because you're always going to be one number behind, right? Okay, good. That's why you see that, just T+1 for size. And also it's empty, just check if T is equal to -1, right? And then for the top, now back to William's concern. Actually, you were talking about push, but top as well. If the stack is currently empty, you should throw some illegal argument exception, okay? And then, always for the top, you always return data at position T, okay? And then for push, now if the current capacity is already reaching the maximum, that means you cannot push anymore. In this case, if I still want to push, what should I do? Let's say I got 1,000 elements already. I want to insert another one. If I really want to do it, I need to grow the array. Grow the array, let's say double the size, 2,000. Copy all the 1,000 elements from the old stack into the new stack. And what's going to be the cost? Linear, right? Okay. It seems like so far, okay, I'll make a mini conclusion in just a moment. Now, for the pop, okay, you got to assign the result, decrement the T, and also return, right? Good. Now, you can see that for every operation we have over here, we don't have any loop, right? So in this case, we have basically constant time operation for all the methods. However, there's one limitation over here. If I really want to store the number of elements that's more than the maximum capacity, in which case it will be very costly. It will take linear time to copy all the old contents into the new stack. That's the only limitation. However, if you use linked list, you wouldn't have that drawback. Because for linked list, you can always just add it to the end, right? There's no space limitation. Okay, so now you can also go over this JUnit test, so you can just go over that, okay? So I've drawn the diagram to show you already. So it's already also available on the source code, okay? Any questions up to now about stack? Yeah?
So to clarify, if you're like duplicating the stack, that's what
You mean, you want to copy a stack?
Yeah.
Okay, for example, you may want to do, let's say you simply want to copy a stack. Of course, you're gonna go over the element from 0 until the top. Right? Of course, that's going to be linear.
Like what we talk about
Uh-huh. The linear, what do you mean?
Like you mentioned that if you
Oh.
do something in the stack is linear, but if you for the link.
For the linked list, we'll get there. We'll get there. Don't worry. We'll have discussion about that. Yeah, in just a moment. I just want to do some preview before I talk about it. Okay. So now talk about array. So now you can see the running time for everything over here is simply constant, no loop. Okay. However, implicitly, if you want to go up beyond the maximum capacity, you have to do copying. And that one's going to take linear time. Okay? Okay, linear time if you want to grow the stack and copy the old contents. So that's about the array implementation for stack. It's pretty good, I would say, but you do have space constraint over there, right? Any questions about this? Yeah?
So when you want to, when you see that it's insufficient and you want to add more
Capacity.
you have to create a new batch.
You got okay. It's a little bit like this. You got to create a new array for data. Let's say you can simply say data is assigned to new data with the size 2 times the maximum capacity, right? Doubling strategy. You will learn more about this in 2011, and then you can just copy everything from the old data to the new data, right? That's what you can do. But since now over here in this current implementation there, we simply say if you already reach the maximum capacity, throw some illegal argument exception. So that's okay. We just make it easier for you. But realistically, you should not constrain the user to add more elements beyond the maximum capacity. Right? Okay, good. Now let's talk about singly linked list. Okay. The way I'm going to present this is I'm going to leave the code to you, but let's talk about the ideas, how you can implement that. It's quite easy, okay? So now, let's see this. Let me just give you the general structure. You're going to declare a similar class, which is called linked stack, which means it's going to be implemented using linked list. And you have just one attribute, which is called singly linked list type and called list. Declare that, and then you can call all the methods that we talked about in the previous lecture, right? Add first, add last, and then add at a particular, well, actually add first, add last. You remove first, remove last. Choose the one that's necessary. So now, any question about this structure here before I talk about how you can implement that, okay? I'm not going to show you the code, but what I will show you is you got two possibilities over here. You got at least two options. So where should be the top of the stack? Should it be the front of the list, the head, or should it be the tail of the list? So, yeah, head or tail? I heard head, and you said tail, right? Justify.
Well, it's last in, first out.
It's last in, first out. Okay, let me tell you this. If you treat the head of the list as the top, that means you're going to remove the head when you pop. If you treat the back of the list as the top, that means you're going to remove the last when you pop. So now, are the running times for remove first and remove last the same for singly linked list? Remove last is linear, whereas remove first is constant. So which one should you choose? You should choose the one that treat the front of the list as the top, right? Everybody follow? Okay, I'll try to go over the slide, but that's kind of the thinking process, right? Let's try that. So now let's see this. So here I'm going to have strategy number one, strategy number two. Okay, for both strategies, whenever you want to get the size of the stack, you can just get the size of the list, right? However, you cannot do this for the array, right? You cannot simply return data.length. You got to return t plus 1, right? Just some connection here. And also it's empty, it's also is empty. Quite nice correspondence over here. Now, let's say over here, you can see that depending on how you interpret the list, you might say the first of the list is actually the top, or the last of the list is the top, right? You got two different strategies, okay? Now, what about push? How would you do the push for the first strategy, push? At first, right? Good, and the second one, at last. Oh, that's easy. What's the running time for both? Constant, right? So there's no difference in terms of this operation here. Okay, very good. And what about pop? Well, you can see that since for the first strategy there, we treated the first of the list as the top. So when you remove the top, you remove the first. And similarly, for the second one, you remove the last. And we know that remove first, remove last for singly linked lists are different in terms of their running time. So now you can apparently see that for you as an implementer, which strategy should you choose? One or two? First, one, right? Yeah, because second one, pretty much the same, but whenever you do pop, it's going to be linear rather than constant. Okay? Any question about the reasoning process over here? Any questions? Okay? Okay, if no questions, I will move on. Okay, apparently you're going to choose number one, okay? Because you want to avoid remove last. Later on, in 2011, you're going to learn about doubly linked list, in which case it makes no difference because for doubly linked list, you have the reference to the previous node, in which case remove last will also be constant. But that's something you will learn in 2011, not this course, okay? So the context is very important. So you can see what we have been doing here. We are not so satisfied with just having one implementation as a choice. We're trying, basically we are covering three different implementation choices. Either you can do an array, or you can do a singly linked list where you treat the first as a top. Or you also have a singly linked list where you treat the end as the top, right? So you got three different choices. You should really decide which one you want to use. Okay? It seems like, so now we got three options there. Which one should you choose? Array, strategy number one, or strategy number two? Array, I heard array. Array is not too bad, except that it has the space constraint. So strategy number one is as good as the array, but has no space constraint. Number 2 there, it also has no space constraint, but for pop, you're going to suffer. Okay, good. Okay, that's kind of the reasoning process you should have. Okay, this one just repeating. Okay, you can read it over. Okay, now there are 2 applications of the stack I would like to go over. Let's go over the easy one, and I will save the second one at the end of the class. That was a little more sophisticated. I want to finish the cube before I get to that second application. Let's see the first one. Let's say this is what we want to do. What you learned so far, how would you reverse an array? You can simply run a for loop, and then you can play with the indices, right? Maybe that'll be data.length minus I plus 1, something like that, right? I think one of the preparation exercises was like that, right? Okay, we're going to learn at least 3 different ways of reversing an array. This is the second one, using a stack. The third way is using recursion, which I'll go over possibly next Tuesday, okay? Now, the idea is very easy. Actually, we have already gone through the idea. If we try to do Alan, Mark, and Tom in this pushing order, if we try to pop, it's going to get Tom, Mark, and Alan, the reverse order. Now, how would you reverse an array in general? Let's say this is the method, the signature. So let's say we just have a utility method here. So we're going to change the input parameter over here, array of string, let's say. How would you do it conceptually? Okay, maybe I'll let other people try. How would you do it using a stack? Somehow you want to use push and pop, right? But how would you combine them in a way that is going to produce the reverse of the array? Let's say the array looks like this: Alan, Mark, and Tom, right? Alan, Mark, and Tom in this order. How would you do it? If you try to push in the order Alan, Mark, and Tom, and you try to pop it again, would it give you the reverse? It would, right? Okay, so that's kind of the insight. Okay, let's try. Okay, let me show you the code, and I'll show you one run. First of all, I just declare an array stack type over here, and it's called buffer, just to store some contents over there. And we got actually basically 2 different stages. Stage number 1, we're going to keep pushing. We're going to go from left to right in the array, Alan, Mark, and Tom, and then keep pushing. Okay? So we're going to go from left to right in the array, 0 until a.length, and then we're going to say push ai. That's the first stage. Let's say we already got Alan, Mark, and Tom, so we got Alan at the bottom, Mark, and Tom. That's what we get. Now, second stage, what should we do? We don't need to worry about this array anymore because we have read whatever we need in order to manipulate, right? So now let's think about this. Let me just show you what we have done so far, okay, quickly. So now let's have a new thing over here, array stack. Okay. Now let's say this. Let's say this is the array. A over here, 0, 1, and 2. And then we have Alan, we have Mark, and we have Tom. So what we have done over here, we say that for integer I, 0 until 2 in this case, right? And they're going to keep pushing. So for the very first iteration, we're going to push the element at index 0, right? It's going to be Alan. Second iteration, we push the element at position 1. That's going to be Mark. And then the last iteration, we're going to push the item at position 2, Alan, Mark, and Tom. So that's at the end of the first stage. Our eventual goal is to modify A such that it becomes its reverse. So now what should we do? But how many times are you going to pop? That's my question. 3 times, right? Depending on how large the stack is. We're going to keep popping. Every time whatever we pop out, we're going to assign back to the array. Okay? So there are 2 different ways to write this. I'll show you both ways. Okay? So now, basically, let me show you, first of all, you can say for integer I, 0, and then I less than, for example, a.length, I plus plus. Okay? Let's try to see if you can understand this particular line. You can say 8 at position I is assigned. So this is stack S. Let's say buffer. Okay, that's what you have. You can say buffer dot pop. So every time you call the pop, it's going to return the top and then remove it. For the very first iteration, what is it going to do? Let's try that. For the first iteration, I is going to be 0. And then buffer.pop is going to be what? Tom. It's going to remove Tom, and then also return Tom over here. And then we assign Tom to 0, right? That's the first iteration. And second iteration, and then the loop counter is going to be 1. And then we have buffer.pop. So now Tom has been removed from the previous pop. So now it should be mark, right? Remove mark, and then the return value from there should be mark. And that means we're going to assign mark to the first position of the array. And then it's going to be mark. Okay, final iteration. For the final iteration there, so it will be 2, the loop counter. And then if you try to pop again, it's going to be returning Allen and remove Allen at the same time. So it's going to be Allen over here. And then we're going to assign Allen to position 2, right? And then it's going to be Allen. And then we are done. Okay? Any question about this? That's one way of doing it. I'll show you another way in just a moment. This one is a little bit from the perspective of the input array A. I'm saying that for how long A is, I'm going to do this many pops. Okay? I can show you another way which is equivalent. Okay? Let me show you another way using a while loop. Okay? Okay, I'm going to use blue here. So you can say while over here. Let me also say integer I is assigned to 0, just for now, okay, in the beginning. While buffer, while it is not the case that buffer dot is, sorry, I'm running out of space, is empty. Okay, that's a condition, okay? While it is not the case that buffer is empty, and notice the negation over here, which means as soon as it becomes empty, we're going to exit from the while loop, okay? And what should we do? Well, similar. What you do inside is exactly the same. You will say AI is assigned to buffer dot pop. Would that be it? Well, I'm missing something. If I simply do this, would it do the job? No, right? It will always assign to 0. Right? Don't forget. Okay? I think in principle, people like the second way better. It's a while loop. Okay? But doesn't matter. It works the same way. The idea is that in the first phase, we only do push. Second phase, we only do pop. Exactly the same number of pop. And because of the last in, first out property of stack, this will do just the reverse. Okay? Any question about the first application here? Are we okay? Okay. Let me very quickly talk about what a queue is, and then I'll talk about second application at the end. Okay? Very quickly. Okay, I'll talk about this one's very interesting. I'll just get to that in just a moment. Okay, let's talk about the queue. And you can think about the way we talk about each operation and the behavior is exactly the opposite. Okay? So again, queue is a collection of objects like stack. But now the way we access the element is different. For stack, it's level, last in, first out. What about queue? FIVO, it's called first in, first out. Okay, level and FIVO. Okay, that's quite a common acronym you have to recognize. Okay, for queue, so now for the stack, we can only access the top. Now for the queue, we can only access the back of the, or we can actually access the first of the queue, the front of the queue. But when we add, we got to add to the back. Okay, I'll show you some diagram. Okay, let's just go over this slide very quickly. So you cannot access any arbitrary elements, but you can only access a particular part. Okay, and now whenever you're trying to remove something from the queue, it's like a real life queue. If there's a customer queue over there, which customer should they serve the next? It should be whoever has waited the longest, right? If they try to implement a customer queue as a stack, I think they're going to go bankrupt for sure, right? They always reserve the one who come the latest, right? So of course, the queue. That's why we got a queue idea. Okay, it's like a customer queue you have over there, okay? Or call center, right? You always have to wait. Okay, let me just show you how you can visualize the queue very quickly, and then everything else is very straightforward. Okay, so now let's go to the next page over here. So how do we visualize a queue? First in, first out, or first come, first serve. Okay, first in, first out. Queue. So this is how I would draw it. I would say horizontal, like that. And I would say queue over here. This is an empty queue. Now, there are two operations we support. I'll just mention that right away. Okay? You can either say queue dot in queue. In queue, so basically it's like an in over here. That means we're adding something into it. Okay, how do we add it? In queue, let's say again, let's try the same three people here, Alan. If you do Alan over here, what you will get is the same queue, but now what you have is Alan is now at the front of the queue. Okay, so now we call this, by the way, let me just annotate that. So this is the front, this is the back. Okay, so now if I try the following, I say queue dot first, it will be just Alan. Okay, it's pretty much like a top, right? So far it's really similar. But now let's try the following. If I say another one, let's say queue dot in queue mark. Now if I try that, what I will get is something like this. So queue over here. Now the front remains to be Alan because he has been waiting longer than Mark, right? So Alan is still at the front, and now Mark will be here. So what does that mean? That means every time you want to insert something into the queue, you want to see where the back is. Insert from the back. You want to get something out of the queue, get it from the front. Okay, that's why it's called first in, first out. Okay, and now over here, let's try another one. If you say queue dot first remains the same, it's still Alan. Okay, queue is very easy. Okay. Any question about this? Well, okay, right? Good. Okay, let's now go over some implementation detail over here. So we got first size is empty just like before. Now we don't call top, we call first. Okay? And also you got in queue rather than push, you got DQ rather than pop, right? Just want to compare. And every time you do DQ, it's going to remove the old front and return it, pretty much like a pop. Okay? Everything is very symmetric, so that's why I don't need to spend too much time on the queue. All you got to remember is the way you update a queue has to be first in, first out. Okay. Okay, you can read it through. It's very easy over here. So now, how do we implement a queue as an array? Okay, it's going to be almost the same. The idea is the same. We want to have also an index for the back of the queue, because every time. Okay, let me give you some idea. Okay. Now the array implementation is also very straightforward. Let me just use one example to show you. Okay. Okay, let's say this. Let's say we have queue over here, and initially it's going to be, let's say also the maximum capacity is 0, 1, and 2, up to 999. Okay? And now let's do the following. Rather than T means the top, as before. Now we have something called R for the rear of the queue. R, rear of the queue. So this tells you where you should insert for the queue. Okay? Let me give you one example. Let's say here. Now if I say queue dot, let me use a different color here. Now if I say queue dot in queue, Alan. Remember, if you want to insert something into the queue, you want to know where the back is. What you should do is, first of all, if you, and R initially also is -1, because in the beginning, nothing there, right? Okay? So now, what you can do is, you can simply say R++, which will change this into here. And then you can do Q, Q at position R, thank you, is assigned to Allen. Basically the same idea as before, okay? And then you can store Allen over here. Okay, and then how do you DQ? You can just decrement the index as well, right? Oh, actually, for DQ, no, it's not that. Okay. Okay, let me just do one more, and then I will illustrate that. Okay, I should not just skip. Let me just do one more. Let's say Q dot in Q over here, mark. Okay. And then I'm going to say R++, and then Q at position R is assigned to mark. What this will do is now R is going to point to this position over here, and then it's going to be mark. Now, question for you. How do we implement the first method for the Q? If I say Q dot first, we know that the front of the Q should be Allen, because he was first inserted. How do we do that? Q at always, right? Okay, very good. Q at position 0, always the case. Now, what happened to if I say Q dot DQ? Which one am I supposed to remove? Am I supposed to remove Allen from the Q or mark? Allen, right? Now, if I simply just do this one here, that's not good enough. You're creating some null slot. You want to shift everything to the left by one position. And time complexity for that. Linear, right? You got to shift everything. Well, you might have a fully occupied queue with 1,000 slots. You're going to copy every 999 element to the left by one position, right? And then this one, I'll just say big O of n. You're going to shift, right? You're going to say shift mark into the first position. So mark becomes the first. Okay. Any question about InQ and DQ for array implementation? Questions? Okay. It's very similar, okay? But they are not exactly the same, but similar. Okay, so we can now go over the code over here. Very similar. You can see now we got R, which is rear index. And then I want you to draw your attention to, when we do DQ over here, we have to run a loop over here to shift everything to the left by one position, okay? And then return whatever we just DQ, okay? That's why for the DQ method here is actually very expensive, okay? So the array implementation for the stack, push and pop are very cheap, only constant time. But for Q, the DQ is expensive, right? There is certain thing called circular array, but we are not going to cover that in this course to make things better. But you might learn that in 2011. If you're interested, feel free to Google circular array or talk to me during my office hour, okay? Okay, you can also go through the test case over here. It's also available in the source code. Okay, let's talk about linked list very quickly, okay? The same idea, okay? DQ, you can see is linear time, okay? Now, let's talk about how we can implement a queue using a singly linked list. The same idea. Do you want to treat the front of the list as the first of the queue, or the back of the list as the first of the queue? Why?
You don't want any keys for the last.
Think about this. If I somehow treat the last, okay, actually, let me just make it visual. Otherwise, I can also get myself confused. How about that? Let's be careful, okay? Now, let's think about this. So we got two different strategies over here. So let's say over here, let's say implement the queue using singly linked list. Let's say that's what we're trying to do, singly linked list. So there's two strategies. Strategy number one. Let's say this is our list conceptually, right? This is our list. okay, like that. And this is the end. Let's say for strategy number 2, let me just draw the diagram. Okay, for both options, we're going to consider NQ and DQ. Let's say, let me use over here, green for the front, okay? Now, you can either treat, oh, by the way, so this is the head, right? And this is the head, and this is the tail. Okay, let's make sure the context is clear to you. You got two options. Either you can say this is the front of the cube, or this is the front of the cube. Either way. So now, in strategy number 1, how do you do in Q? At last, right? You simply just add something over here, right? What about second one? At first, right? That's also cheap. Add it here. Both are cheap. You cannot see any difference yet. Now, what about I want to do DQ? Remember what the DQ is supposed to do. It's going to remove the customer who has waited for the longest. So that means it's going to remove the front of the queue. Now, for strategy number 1, which one do we want to remove? Well, the head, right? Remove first is cheap. What about the second one? Tail. How can you remove the tail? You cannot remove it right away, right? You want to figure out what the previous one is and set it to be the tail. And it's syncly linked, so no way. You want to go all the way to here, which will take linear time already. Okay? You can see strategy number 1, strategy number 2, they are somehow different, especially when you do the DQ. Is it clear? Okay, good. Let's go back there, and now you should be able to follow the slides. Okay? Okay, so now you should be able to. Okay, now let me use the remaining time to show you some interesting application for stack. Okay, before I go there, any question about Q? Okay, if no, I will go back to some interesting application here. In some way, that's part of how Eclipse is implemented. Part of. Matching delimiters. Of course, it's a simplified version, but you get the idea. This is a problem. Let's say we got something called opening delimiters and closing delimiters. You got parentheses, brackets, and let me use this way: round parentheses, square brackets, and curly braces. Right? You can see these ones are opening, and they have some matching ones. Right? So, for example, this one over here, the left round parentheses should match the right round parentheses, and the left, the opening square brackets should match the closing one, and also the opening curly bracket should match the closing one. Right? Okay. So now, what do we do? Let's say I want you to implement a method which will take a string, and the string contains these characters only. And then your method is going to figure out if it has matching delimiters. For example, let's say this. Let me just draw that, okay? How about that? Otherwise, it may be difficult for you to see. Let's see some valid and invalid one. For example, if I have something like this, this, matching, right? This matches that, this matches that, this matches that, yes. Another one, this, matching, right? This matches that, this matches that, this matches that. Okay, let's try something that may not be matching. What about this? No, right? This one is okay. This one here is okay. But this one here, no. Somehow this one, this and this, they don't match. So no. So this is one occasion where you might get errors. You might get, you have to return false. Let's see another occasion, okay? Let's say we have this, and this. Somehow this matches that, this matches that, This one here has no opening delimiter left to be matched, right? So this one also no. One more example. What about this? This, and then this. Also no, right? This matches that, and this is some opening but has no closing one to match that, right? Also no. So these are kind of the categories of cases you have to handle. Yes?
What about the case where you put it overlapping?
What do you mean overlapping?
So you put like the round bracket inside the middle of the three square brackets.
Second last. Oh, you mean something like this? You mean this one here? You put,
I want the second last example.
oh, second last, sorry, I didn't hear it.
The
Mhm.
opening brace, the round one in the middle of the two square ones.
That wouldn't work. Okay, okay, I see what you mean. Okay, let me try. The question was something like this. This, good question. Put it here, right?
Yeah.
Very good question. That one there is going to be something like this. Okay, actually you're forcing me to tell you how to solve that using a stack. Okay, why don't we try that, okay? There's a good example there. First of all, it's not matching, right? Let's think about how you can use a stack to do this, right? Basically, you're going to start with empty stack. Every time you see some opening delimiter, push that. Keep pushing until you see the next closing delimiter. You want to see if the top of the stack is matching the closing delimiter you're reading. If they match, you can pop off the stack. That means that part is matched and reduced. Okay? Let me show you an example. Let's see this example in particular, how will we do it? Empty stack over here. Now, this is opening. Read it. This is opening. Push. This is also opening and push. Now, this is the very first closing one you're reading. Now, is this matching the top of the stack? No, it does not. So, return false. It's a little bit like a category number one. A little bit like that. Okay, let me try to use a stack since I already talked about stack. How would you analyze this case over here? This one over here. I'm going to write it here. You have that, and that. Okay? Let's use a stack over here. Reading opening, push, reading opening, push, reading a closing one. Does this match the opening? It does. Pop it off. And now, does this one, also closing, match the one on the top? Yes. Pop it off. Now, you're reading a closing one, but now the stack is empty. You simply have nothing to match. So when you have a closing one, but the stack is empty, that's error. Okay, let's see one more. How about the last one? When you have, let's say, use this color over here, you have this, and this. Now, similar, okay, let's redo it. This and this, right? The first two, they're simply opening. Now, closing one, which matches the top, pop. Closing one also matches the top, also pop. Now, you got another opening one, and you push that. Now, you're reaching the end of the string, and the stack is not empty. That means that also doesn't match. Okay, so this pretty much illustrates the Java code already. I want to show you the Java code and just tell you one trick over there. Now, the question is, when you, for example, when you see that the current string I'm reading is actually a closing delimiter, how do I check it is matching this one over here? There's a clever way of doing this, okay? Think about this. We define two constant strings. Let's say one is called open over here. So curly brackets, square brackets, and round brackets. And also you got something called close. And curly brackets, square bracket, and round brackets over here. You can see position-wise, at position 0, they match, right? And at position 1, they also match. And also at position 2, they also match, right? What you got to do is, you want to check the index of the closing one you're reading. Let's say it's index 1. And then on the top of the stack, check its index of the opening one. If the indices match, that means they match. Okay, that's the only trick for the code. Okay, now it should be able to, let me show you the code very quickly and then we are done. Let me go back there to the, oh, actually, sorry, not this one. Okay, you can read through all the description here. And now, one more thing for you to think about. You might think about why can I not use the reverse method to solve this problem here? Okay, I'll leave this to you to read it over. Okay, you just cannot use the reverse. I'll leave that as a self-study. You can think about it. Okay. Now, when you see the code, it reflects exactly what I just said. You can see open and close strings. All the source code is available on the course website. Read it, and then we're done with stacks and queue. We'll do recursion from Thursday. Okay, see you.